Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger and disassembler. Today is a special day because it's gonna be a demo. I don't know if it's called demo, I don't know. But yeah, it's gonna be a demo stream, and what I'm basically gonna do today is not programming at all, but just to show you what I've been working on since last month, um, throughout all this month, and yeah. So if you guys remember, the last thing we did was that we um, started to make this specification, and let me show you here where you see some data. Basically, what I've been doing through this month was, first of all, continue with the specification. If you can see, it's all this stuff, it has the basic stuff. It's not complete, of course, but the thing, the main reason why we started to do these things was just to understand, like, okay, what was the problem, since specifications let us and help us to understand the what, you know the what of the problem. So with this specification, we found that, and we answer the what's the problem. What does the disassembler do, and basically it explains it in a really we can say explicit way. Where you say, we have these bit fields, and this translates to this assembler syntax, we can say. So that's all what we can see here. For example, I know the RM field, which is that some instructions have them. If they have a mother RM field. So the RM field, you can just say, and you see here, it's just like a table thing. It's like if I just read the specification and pass it in a formal syntax into a language. This is not this is not C, but it's just sufficient to see what we want to do from it. So yeah, it's pretty simple. It addresses pretty much, I believe, in this part is 32 and 64 for the modern bytes. It's all the table just as a switch statement casing. And pretty much, all the specification, it's full of switch statement casing. Yeah, and that's pretty much it. I can show you pretty simpler ones. For example, the E fields, SREC fields, SREC3 fields. So the main purpose is just to specify what all tables from the Intel IA32 and x64 manuals to give to us, just to put it in a switch case statement. That was the main purpose of doing this. So to see how easy was for us to understand the data, to see the tables, and and in as the same way to be executable, which is the another reason why we did this kind of specification, which is it's not a formal, but it has a formal syntax, we can say. And yeah, that was all for it. And yeah, here we have some examples of what some instructions and what does it mean, which is pretty it tells us pretty straightforward what we wanna see, what does the disassembler does when we, let's say, it finds this bit field on the bit stream, whatever it finds it. If it finds it, it's just a simple switch case statement where it says, okay, if you can find this, just print this. This format near jump EV. And if you guys have followed the streams, we know that the EV, it's a modern operand which has 1632 operand sizes. That's it. And we have these flags. The nice thing about this form of the specification is that we can see pretty easily how or what, let's see more what, because the specification is what does it do, what exactly does it do when one instruction gets executed, instead of having all the marasm of making all the compression, like compressing all at once, like the thing we had before, like saying we want to disassemble all the things with the same code patterns. We now the problem, it's spread all into instruction problem, so that instead of having just one loop that disassembles all instructions, now we have the same loop, but we have a case statement, a simple switch case statement that disassembles all instructions. If we find this one, we get this one, and then for getting the symbols for that instruction, we just execute them serially. You say, oh, okay, yeah, okay, this instruction is it's forced to 64. This is what it means, and then we get the operand size, the effective operand sizes of them, with that, if we have a prefix or something. And then we have this is not supported for the processor mode 64. I believe is yeah, it's not supported in 64, or it's not supported. It was not supported addresses. Well, let me check it out. This was a function. It was a support function. I don't know, where is it? Can see. Here you go. Yeah, in the case instruction syntax that requires an address override prefix in 64-bit mode and is not supported. Using an address override prefix in 64-bit mode may result in model-specific execution behavior. So the specification has all these kind of tricky rules about the instructions, so that it was just way more simpler to just have a switch case statement for each instruction and have each instruction do whatever he needs to do, for disassembling it, So if it tells, if the specification tells us, oh, it's not supported because of blah, well, we can do it pretty easily because we have the specific case for each instruction to handle it, That's all it is. So that's it's a pretty simple change here, but it makes a whole lot simpler this stuff. The problem, instead of being a lot of ifs and patterning, it's just a switch case statement that you just follow through, and that's it. So that's pretty much it. That was the pretty much change that we made to the disassembler itself. It was like, first try to understand the problem. We found out that the problem was an instruction problem. It was like, okay, we got this problem. We got this instruction. Tell me how to do disassembler, and that's it. And yeah, I just have here the jump instructions, but this is the first thing we did on this month. But now I'm gonna show you the real thing. This is not all, man. This is just the first part. So if you wanna stay with us, just follow us, because we're gonna show you the real thing. So as I explained here, this is just the specification. It was just like we can say like a exercise, an example of for me saying like, oh, what could it be, without having the marasm of like getting the specifics real about the syntax, like using C or any other language. I was just like saying, okay, let me write this in a language that it's free for me to just write, and it doesn't matter that it's not even a language itself. It's not even a formal language. But this is a really important thing to do in programming. It's the first time I do it, but actually I believe it's really important to do this kind of stuff more all the time. If you have a problem that you don't understand, making a specification of it is super important. It's like saying, I don't understand the problem. Well, let's write what does the problem do, and let's write it in a syntax that I can understand easily. That doesn't happen that doesn't need the rules of a language, because a language limits you on the constructs that you can think about. It's like saying, I don't know if you have heard about this, but I mean, a language shapes the way you think. So a language shapes the way you think. If a language shapes you the way you think, then you can just think in the way that you use the language. So that's why I didn't. That's why the first time I did this, I chose not to use C as a specification language, because I was just trying to think about it. And it's better for me just to think it in a language that I can just express it. If it was later on to see like it was a little bit more formal, it's because it's better to think it more in the programming syntax way. I don't know how to say it. I mean, formally it's called formal syntax. So this is a formal syntax. It expresses things in a real concrete way that is not just a natural language, as English or anything else. So it's something that it's more simpler. It's a context-free grammar. It doesn't have any context. So that's really important. It's just to show you how to do things that, or at least to show you how I did this. How I solved this problem. And probably, I mean, I'm not saying that this behaves or solves all the problems that you can find or you will find out in programming, but at least for this specific problem, it was just awesome. And that's it. I think that's really important. To define the problem first, especially when you have a really complex problem like a disassembler. Where you have like all these petty rules, and really, I mean, you cannot get it through all the manuals. This was the first thing to do. I got a full thing of the specification. Telling me like in one page was one thing. I mean, the whole thing of making the abstraction of it and just comparing up to this specification, it was super necessary. It was paramount to do this kind of stuff. So anyway, so once we did that, the thing that I did was that to pass directly the specification that I got here to C. And I mean, that was pretty simple because since this is a context-free grammar, or it looks like that, it was pretty simple to just use the same thing and just pass it to C. And it was pretty simple. I mean, it took me like 2 weeks. 2 weeks. I mean, 2 weeks of translating it and disassembling like 4 instructions. And man, this was super fast. I mean, if you remember the first time, I mean, if you have seen the streams, you've seen like in the past we took like months to disassemble some instructions, like 2 or 3 instructions per month. And now this assembler 4 instructions in 2 weeks. And man, that's really crazy. I believe, I mean, that's also really important. How much time you deal with the problem, and the way you if you understand the problem, of course you're gonna step faster on it. You have something like this assembler, you have a lot of instructions happening to have all the syntaxes and have to put all the syntaxes. You have a way to put it really fast, then you've gotten a step forward into it. You have solved the problem, and you have gotten efficient into doing that kind of stuff. So actually that's really good. I mean, that's another point to the specification, because using this syntax was just like, I mean, simple copy paste of doing it. I mean, each instruction, I can show you. I can even show you one. Where is he? No, I lost it completely. I think it's it. Yeah. So let me show you. What I started to do was like I have this PDF annotator that I basically just I started to. I mean, I just got to the point like, I mean, this thing seriously. So I'm just trying to mark up all the instructions that are already done. And this is one of them, the beat test. We have other ones, but the thing was like, I mean, I just basically took each of these encodings practically because that was for free, you know. I mean, the specification already give us this, you know, and this is and we can take it for real, you know. We can take it this like this is the real thing. So I basically took each instruction and just copied this, and I put it into this CPP file, you know. I basically copied the specification, translated it, you know, to C syntax, pretty straightforward. And what I did it was this, you know. If you remember, we had, let me show you. For example, let's say we have this GCC here, and the GCC here that we have is this one right here. So we have this GCC that matches to this GCC, and if you see, I mean, it's pretty simple. I mean, well, it's pretty I mean, it has the same format. It's just like, you know, it has some extra things that we need to do so the implementation specific, you know. But that's it, you know. I mean, it's not anything crazy or anything like it. And such as it's the same for each instruction that I have disassemble, you know. Dun, 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 dun. You know, we have a pre-switch case statement here, you know, per instruction, and we just follow the through. We just follow it until we get a real match. And I mean, that's pretty much it, you know. I don't have anything special about it. I just have a this support function that's the eval bits, which basically makes all the work pretty much. You know, it got just a bits array, which is this one, you know. It fills it, you know, it gets it, and then it starts to making the match. If it's a bit, an opcode ID, and all the bits are correct, then it processes to do the disassembly for that instruction, you know. And that's it, you know. It's pretty straightforward. Yeah, you know, super simple, anything crazy. And you know, we have these get bits, which is a really simple way of doing a bit fields, you know, to fetch the bits from a bit stream. It's something that I found out from Mr. What's his name? It was I forgot his name. Oh my god. It was, let me show you. Where is he? This is is the rig block, you know. This guy is awesome. And actually this is the block I saw, which is buffer centric IO. If you have time, just check it out. It's super cool. It's Fabian, Mr. Fabian Jason. I don't know if it's pronounced Jason. I don't know, but this guy actually, I mean, he explains a lot of things. A super cool thing about compression, computer architecture, graphics, and I don't know if you are into that thing, just take a look. It's super cool. It's called the rig block, and you know, this is the idea that I follow up for getting the bits. You know, it explains. Well, actually, this is the back end, we can call it, and this is the front end of how we're filling the bits. Actually, I used this kind of variant, which I was like picking the bits, consuming the bits, and getting the bits. It's super simple, super fast, especially because I do a lot of these things. It's super useful for the disassembler. And yeah, I mean, it's I'm not gonna explain it like thoroughly this, but if you want to take a look, just follow the read block and you can read it. So I basically use that to reading the bits, getting each bit, and filling each bit field to getting the match, you know. And you know, it's super simple because once I get the bit fields, I can use them for the specification, you know, for each support function. I can just go into it and make the disassembler for each instruction. For example, the GCC that we had first, let me find it. There you go. You have the GCC, and this instruction, you know, it's pretty simple. You know, it has the same supports, the F64. It doesn't have a W bit present. You know, get effective operating size it was the RM one that I showed you before. You know, it's the mother and byte table, simple. No, actually, oh no, I'm sorry. Effective precise is the effective precise. My bad. No, this is this doesn't have a mother M, so yeah, I was bad. But it just gets a conditional code for it. It's a simple table there. And that's it. For each bit field, it just matches the thing that it needs and goes and looks for it into the tables. As we can say. And yeah. For example, let me show you one that has a mother arm. For example, this one. This one has a mother arm, which is a move, and get addressing mode is the mother arm here, and get rec is just the rec field that it's in the middle between the mod and the RM, we can say. And yeah, once we get the right string, this returns string, we just print it out. Pretty straightforward, and that's it. And well, let me show you. Well, I'm just gonna stop talking because I don't know. I think it's better to show you. So I'm gonna compile, and this is it. Let me show you what's gonna happen here. I have a lot of breakpoints, but that's okay. So this is the bit stream. This bit stream is for 32-bit mode. It's a compatibility mode, and you see here, well, we can see that it looks pretty much the same as the stream we got before, but now we have more instructions, and we are sure that these instructions are correct because we use the specification for doing that thing. So I feel more confident now that we have a real good way to match the instructions. And in fact, well, for a plus, I just make the match with side disassembler, so I can just see like we are doing the right thing. So for each instruction, I just put it on the side disassembler. Actually, well, I don't have it here, but I just make the comparison for each instruction, and that's it. Pretty straightforward. For example, you can see here we have the inks instead of the rex prefixes. That's pretty common for a 32-bit string field. 32 bits code stream, we can say. So yeah, so this is like the reason why we can see like this is a 32-bit stream, and as well we have some instructions there. All the ones that I've done right now. Some string instructions, some bit test instructions, an add, some increment, decrement, some move, something with rep. All the prefixes now are done, which is good. Before we didn't have that thing. Well, no, I'm sorry, I don't have all the prefixes, but I have some of them. My bad. I have the reps. I have the address override, the segment selector overrides, so that we can have, instead of SS, ES, or anything else, if the instruction supports that, of course. And I have IMO instructions, the jump that I showed you before, jump on comparison. We have that. I have the decrement, all their moves. I have forward jumps, and I think that's it. So yeah, and all addressing modes as well, with REX and stuff, which it was the thing that we already had before. So I mean, the same stuff that we had before, I just pass it and do it again, but now with specification, and I don't know how many times faster, but in 2 weeks I just did everything back again, and it was way much faster. So I don't know, guys, but I think it's gonna be really good. I can see the thing going. I can see the work flowing. So that's good. And in fact, another nice thing about this is that, I mean, this is in 32-bit mode, but I can change it to 64-bit mode, and it's just gonna be the same. I don't have to change anything. The specification just works for both. so you don't have to care about that because it's already solved. So if I change the mode to disassembly, the disassembly mode to, well, the processor mode to 64, I can show you. So for right now, yeah, you can see now the increments and decrements that match the REX now are gone, because now we have REX prefixes that are valid. So that's the most relevant thing that you can see that differentiates between both streams. This increment, of course, is the one that is valid on 64-bit node that uses the memory operand, and it's actually the extended opcode. Yeah. And yeah, I mean, all the instructions are the same. Now we have extension for 64-bit mode prefixes as R13 and all the RSP things as well. This is a 64-bit stream, you can see, and it was just for free. So I mean, again, I'm just like I kind of stopped saying about the good things about the specification. It's just like pretty much important for this kind of system just to have a real thing, a concise and real thing that explains the problem. It's just the thing that we need. It was just the thing that we needed, and yeah, so please, if you have any questions, post them on Twitter, YouTube, or the Handmade Network forums as well. I think that's all. And yeah, I mean, that was the demo for this occasion. I believe I'm gonna continue doing demos. I think that's so just that to accelerate the process of making this disassembler. But please, if you have any questions, I will be really happy to answer them. Of course, I was just really eager and excited to show you this, so actually that's the reason I made the demo. And yeah, that's all for it. So yeah, so thank you very much for coming up to this demo, and I will see you all on the next stream. Thank you. Take care.